Hi, hello again. Thank you. So this presentation is around boosting performance in Pulsar 3.0 and further on. So this for me was like a very fun talk. I could put material like there for like six hours, and but yeah, I had to trim it down to 30 minutes. But I do have a lot of slides, a lot of material here. The first question that I want to answer here is why to invest in performance improvements? Typically, like you always have like trade-offs. Like, should you optimize this part? Is it good enough already or not? You can just add more nodes and that's it. So there's always like a diminishing point of return that, okay, it takes this amount of engineering time to do this optimization. Is it worth it or not? And I don't think there is one single answer there, but it's like one point that I think is worth is always like to consider whether this open up any use case that it will not be able to do it without this improvement. So does it tip the scale in favor of like, okay, this use case now it is possible, it is feasible, it doesn't make economic sense, when before it didn't, because you need so much resources that was not possible. So in all these cases, I think the answer could be yes. Another way to look at this as there are multiple ways that a system you can use a system like Pulsar, and of course throughout the years we had optimized for certain use cases, and you can see that Pulsar is typically very efficient when doing things that are transferring big chunks of data. So everything is done with the minimal overhead. We don't copy payloads. We don't allocate memories and all this kind of stuff. To achieve those conditions, you typically have to do something, and essentially you have to pipeline a whole bunch of data and let the batching that is done by the client SDK to be maximized so that you can have bigger batches and concentrate the throughput on fewer partitions. So in some cases, it is natural for a use case to achieve those goals. In some other, it can be trickier to get them. And in many cases, the CPU usage in both Pulsar and BookKeeper it is dominated by it is determined by how many batches per second. The reason is that there is a lot of like RPC involved per batch. So therefore, if you have few bigger batches, the CPU work is that okay, copying a big buffer, but that's very efficient compared to many small batches. You have to do a lot of RPC, which are much more expensive. But so to achieve this good batching factor, you need to basically first use the send-async API, which it can be tricky, and pipeline, and so on. The other one is the reasons where it's difficult. So async publish can be very difficult. So you have to design your application to be asynchronous. It's not just like publish and wait and block the thread until the message is published. You have to send a sync and then track the callback. Now, for many developers, it's much more complex. So they have to reason about, okay, what do I do? The response is coming from a different thread. What do I do my pending request? I have to think about what to do with the back pressure on their application level. So client SDK handles back pressure, but you have to reason, okay, when async send is blocking or when it's rejecting the writes because the number of sending requests is full, is already filled up and so on. And the other part is that sometimes the traffic is naturally spread across multiple topics. So there's not much that you can do. The traffic per topic is lower. Therefore, the amount of batching that can happen is smaller. And I just do a quick recap on how batching works in Pulsar, just to give you more insight on why. So typically, an application developer will just use send async, and the messages are basically queued up in the producer, in the client SDK, And you can give basically a time budget, for example, like 5 milliseconds. Everything that comes in 5 milliseconds gets packed up in the same batch. And there's also max size of bytes and number of messages. So once the batch is ready, either by time or by size, then it gets compressed. And then it gets sent out in one single shot. So I'm not even getting into compression, because compression is very hard to benchmark in a way, because it really depends on the data shape. And it can vary. Like with batching and compression, typically you can achieve like 5x reduction for things like JSON when you have a lot of repetition across messages of the same fields names, for example. But yeah, it can vary a lot based on your data distribution and skews there. But just to visualize, like if you have a single partition, for example, like essentially this becomes that in 5 milliseconds you fill up a huge batch, and that becomes very efficient. But now if you have many partitions, now the same time budget of 5 milliseconds means that you have one message per each batch, because the throughput per partition it is much lower now. Therefore, the size of the batching is lower. Now you have many more batches and much more CPU usage. And just to get a bit of example here is, imagine that you have like 100K messages coming in. You're using a batching time of 10 milliseconds. Depending on your number of partitions, you end up with different rate of batches per second. So with one partition, rate per partition is 100K, average time. So each message will have 1,000 messages. Each batch 1,000 messages. Therefore, you have 100 batches per second, which is very low, and it is super efficient. Now, if you go on the end of the spectrum, now you have 1,000 partitions. You end up with having one message per batch, which is kind of the worst case scenario here. And now you have 100K bytes per second, lots more CPU, a lot more contention in the brokers and the bookies. So how do we go to identify bottlenecks? Like you say, okay, I try to publish on many partitions, on many topics, and the performance is lower than if I'm using a single partition. And there are kind of like a few different classes of these bottlenecks that we can identify. So first one is like throttling. There are many places in which broker will apply. Brokers and BookKeeper and client will apply back pressure at every stage. Typically, you want to limit the number of outstanding messages or outstanding bytes to the next stage. Because if you don't, then basically you have to buffer memory, and that you just blow up eventually. So there are different settings that you can control this. And for example, like in the Pulsar, you will use the Pulsar queue size. In the broker, there is a max memory limit that outstanding from brokers to bookies, for example. Bookies also will have like a journal size and other things, and write cache. So all these settings, eventually, if they're too low for the particular throughput use case, they can limit your throughput. And you might say, okay, my CPU is not maxed out. My storage I/O is not maxed out, but I'm not able to push more. And in some cases, it can be due to these configuration options that you have to understand where is the problem, and try to increase, and making sure that we have enough room, enough buffer for things to go there, and to not be throttled there. The other one is like high CPU usage, and this typically is clear. You're doing more stuff. You're like doing more RPCs, more serialization, more work that compared to before. So you can run a profiler and see what does that look like, and identify the hotspots and things that could be where to concentrate the effort there. The other one is mutex contention, number 3. So mutex contention can be a bit trickier. Sometimes, like, okay, you have a mutex that is, you have like 16 threads trying to acquire it, lots of time per second. It's very easy to spot. In other cases, you don't see it because, first of all, like the impact of the mutex contention, it is non-linear. Sometimes, like, you see lower throughput, and but you don't really realize that because you're not maxing out the CPU. But the reason you're not maxing out is that because of the contention, basically all the threads are backing up and doing waits and then just stopping there. So it's a bit harder to see compared to CPU usage, like in general, like a normal CPU usage, because this is just getting maxed out by all these wait effects and depending on the interaction between threads. And number 4 is a similar problem, but like we have many cases in which we have to basically jump from one thread to another, like basically pass one task from one thread to another. And essentially, this becomes a kind of like in Java is executors. Then you have basically it is implemented with a thread pool and with a queue. Now this queue also becomes a contention point, but because it is so pervasive in this architecture, this message passing between threads, it can become a lot of a very important bottleneck point. So to go to reducing CPU work, the first tool here is using profilers. So profilers, I'm sure like many of you will be familiar. You just like run a profiling job either on BookKeeper or the client or the broker, and you get this frame graph, which essentially it is. For those of you not familiar, basically on the x-axis you have the 100% of the CPU usage, and on the y-axis, basically this is the stack traces of the places where the CPU is used. So the wider means the more time is spent there, and it is based on percentage. So you can even have these with all the threads combined, or like per threads, and seeing different things. And in most cases, you will just want to click and drill down, and you can see everything from like the green parts here. The green bars are the Java code. The red one are the C++ or C code, either JVM or not, and the orange one are the kernel time code. So in this case, you can see that it goes on a write on a socket, and then it spends time there in the TCP stack of the Linux kernel. So running like all these analyses, and it's kind of like an iterative process, you kind of like see that there are a few different things that are dominating in both BookKeeper and Pulsar. And mainly, there are lots of time spent in writes to sockets. So too many calls to writes, and makes it less efficient on the TCP stack, but also on the crossing the boundary between user space and kernel space. And system calls are very expensive, and making too much of them with very small payloads, it becomes dominating factor. Another one is buffer allocations. So for all the buffers, we use Netty, which has its own buffer pooling. Essentially, Netty has re-implemented the JMalloc in pure Java, and so it doesn't touch the JVM GC, but still there's overhead. So allocating buffers is not free. They have thread local pools and all this optimization, but still allocating one buffer and getting back to the pool, he has non-zero cost, and actually can be quite significant. Another one is like thread local. We use thread local again, as we introduced in the past thread local as a quick ways to do optimization that was faster than before, but still thread local can be quite expensive. It is not like reading a number variable. There is some volatile. So if you're doing a lot of these thread local read and writes, it does really impact. And finally, like number 4, we've seen a lot of time spent on executors. Again, it can be due to contention, like when putting a task on an executor, or contention between the threads putting task and the thread consuming task from that executor. So I talked about TCP packets and system calls. So one of the reasons is that we use Netty and we use typically write and flash. So write and flash means that whenever you start to send a message or one batch with one message or one acknowledgement, every time we write on Netty, we write in Flash because we don't want. So Netty, you can either like do write, or write in Flash. So if you do write, and then Flash, you have to kind of like keep track. Okay, I did 10 writes, now I have to issue a Flash. But because Netty will not Flash automatically otherwise. So because we want things to go out quick, basically we're just calling write and Flash. And ends up that each time you do a Flash, Netty will issue a system call right on the socket. And basically it ends up that even if you write, say, 10 bytes with Netty, it just does issue one write. And because we don't have any the nego argument is disabled because of latency, then basically it just goes out one packet, one TCP packet. Now, it is not just like the system call at this point, because the packets that are sent out by the clients or by the brokers or by the bookies are tiny packets. Now, the TCP stack now it has had to basically do a lot more work when interpreting those packets compared to if you had like just one packet with many frames on it. So it's kind of like ripping effect of many syscalls, lots of small packets, lots of CPU in every part of the stack. So first improvement we did was around using a consolidation filter. So essentially, yes, we use bright and Flash. We issue a lot of flashes. But in the Netty layer, we can put a filter there and essentially group all these flashes and optimize out and only send out one. Now, we don't want to increase latency, so there is no like timer that waits and then it sends out. So instead, what we use a trick that is basically like the flash happens in the same thread. So the first one will schedule a task, and that gets executed back in the same thread. So if the rate is low, essentially there is no latency overhead. But if the throughput goes up, now by the time you schedule the task and it goes back in the same thread, you had accumulated a bunch of other flashes in the same queue. At this point, basically, we issuing down one single flash. Basically, we can get rid of tens or hundreds of them. So that reduced a lot the number of. So it's kind of adaptive by nature. So throughput increases. Basically, we could just group more of them. So the result is that now the TCP packets are way bigger, can be like several kilobytes, even if you send like many of 10 bytes messages, and CPU went lower. So this change went in the clients, bookies, and brokers. Another one was reducing a buffer allocations. Again, this comes from one thing that Netty kind of like encourages you to do. So if you look at BookKeeper headers, for example, like this is one part of it, but we have a bunch of different header sizes, right? So we take the payload, which is the thing that the application sent to Pulsar, and then we basically have to prepend a bunch of headers. So there's like a size header, the add request when we want to write on BookKeeper, and then there's a checksum. In the past, we used to do, okay, I need 8 bytes buffer for the checksum. I can allocate from Netty buffer one buffer, use it, and then serialize, and then Netty will just release the buffer, and then it goes back to the pool. Now we have basically 4 allocations per each message, per each batch. And it's true that the payload itself was never copied or relocated. We were using the original one from the Pulsar that gets that hits the broker, but we have all these very tiny buffer allocations. So realization it is really that with many tiny payloads, these allocations become the dominant factor. So we don't care at this point about copying the payload. If the payload is small, we don't care about copying that. If the payload is like 200K, yes, we don't want to copy it. But if it's 1K or if it is 500 bytes, then we can just do a copy. And copy is more effective than just allocating and then referencing a buffer instead of copying it. So But basically, like all these things were done based on the encapsulation. So netty, we want to do, okay, I have this thing, I want to send it out, add a header, and allocate one buffer for this. Instead, what we do is kind of like break this encapsulation a bit and treat the entire thing as a single buffer. So if you have below a certain threshold, everything gets allocated to one single buffer, and it gets copied into it, and then it gets sent out as a single buffer. Another one is thread local access. So this is one example, and again from the flame graph. Essentially here, like, almost 30% of the time was spent in netty recycler. Now we use netty recycler for a bunch of things. One is netty byte buffer pool using recycler, but we also use recycler manually by doing like thread local access, for example. But 30% is spent on this: get an object from the pool, put the object back in the pool. And one example that we did, the change was around the CRC32 verification in the BookKeeper client. Now, this was basically using a thread local object to keep the state of the verificator, and basically to reuse the same object for each digest manager. Now, we kind of like changed the implementation of it and the API to such that the state does not have to be kept in the thread local state. Instead, you can just pass in your earlier CRC, because CRC is kind of like you can resume, like start from zero, compute the CRC of a bunch of bytes, and then compute the next stage, and in which case you can pass back the previous results. So just by changing that interface, that API and implementation, now there is no more thread local access. So the first one, when we started, it was the blue one, and we have buffer allocations. Then we switched to thread local buffers, and then the latest one is like with the no thread local, and you can see that it's a huge improvement there. Now, the other one, which was a fun one here, is improving sort. Again, this looks like interview questions, like write a quick sort. And sometimes there are good reasons for implementing quick sorts. One example is in BookKeeper, in write cache, we have an index that we store as an array. So it's an array long, but each item is 4 longs. And we want to sort it to write the data back in a particular order on disk. You cannot use just JDK sort, because we just sort one by one and not 4 by 4. So we had a group sort implementation. Now, that group sort, the initial code has a problem because the quick sort was manually implemented, and the pivot selection was bad. Therefore, like if you hit it with the pre-sorted array, the throughput was very low, the amount of time that it takes to sort it. So in this case, the lower is worse. So higher in this chart is more operation per second. So first we fix the pivot, and then we do some other micro optimization, like using static methods or like unrolling loops and so on. But because of this function is like so critical that it's used to sort like very large arrays, that it had a very noticeable impact on it. And another fun one was thread synchronization. So we say that whenever a request goes to Pulsar, I mean from the client SDK to the Pulsar broker and then to BookKeeper, it travels within each single process. It travels along multiple threads. Now there are different reasons for having these threads, but mostly it's like for different purposes. So Netty has its own thread pool, BookKeeper has its own thread pool for keeping things ordered in a certain way. And you have to cross these threads because, for example, like this is one example on the right path. So you get a request, it goes on a Netty thread pool. But now you have to switch to a BookKeeper thread, which is ordered by ledger ID, for example. From there, you have to write to bookies, and to write on the socket, you have to be on the Netty IO threads of this TCP connection. So you have to jump on a different thread, and then you can write on the socket. Similar, on the way back on the response, you get responses in netty IO threads. And now you have to jump on a BookKeeper thread, which is hashed by ledger ID. And from there, you have to jump on a Pulsar thread, which is hashed per topic. Again, to have all the responses in the same order per topic. And then again, on a netty thread, again, to start on the socket. So it is a lot of thread jumping. But in a complex application like the broker, it is unavoidable. I mean, you could use one single thread for everything, but that doesn't scale. Now, if you see a queue, essentially you have threads that are submitting tasks to the queue, which becomes a contention point. The more the threads, the more contention you have. You also have one single thread queuing from that queue and taking task, and then we do something. But in most cases, the consumer has to synchronize with the producers, because if the queue is empty, you have to wait there until there is one next task. If the queue is full, you have to unblock the next producer so that you can send the next task. So it is all interconnected there. So one way that we have been trying to improve the situation was adding this batch blocking queue. So batch blocking queue, essentially, we extended the blocking queue interface by having a put all and a take all methods. So now you can instead accumulate a bunch of stuff in your single thread, a bunch of tasks, and then submit them all at once. And similar for the consumer, you can take all at once. Also, it is using we are using array instead of like lists and so on, so that we can basically doing very, very fast system array copies in and out of this queue. But essentially, like the main goal here is to amortize the access and when inserting on the queue and the queuing, and minimize the time of the contention, but still retaining like individual access to each single task. And one of the results here was, again, higher is better in this chart. But we started with a JDK array blocking queue, which was the standard blocking queue in Java. And this basically is a test that passing back and forth from one thread to others, right? But we can have like a 20x improvement from JDK array blocking queue just by transferring multiple items at the same time. We also did a lot of tests with other queue implementation from Disruptor, JC Tools. There's a bunch of queue implementations. The results were always very much lower than the JDK implementation. So I think that also has to do with the newer JVMs. I believe that many things changed in the past years around this. So. But yeah, in the end, so we switched a bunch of components in BookKeeper and Pulsar to use this, and it can be a bit trickier to use on the put all side, because you have to accumulate some items and then send them at once. But yeah, it makes things much more faster. So with all these changes, just to get a glance of where we were and where we are now. So with 3.0 and 3.1, we did a bunch of tests comparing old version and new versions. So this is like the latency on a single topic. So this is kind of like the best case scenario, right? So we have a lot of batching, and so there shouldn't be much difference. And we can just see that the improvement like 0.5 milliseconds in the latency curve across all the quantized spectrum. So this looks better, and it looks improving, but it's not drastically different. But if you are looking at the worst case scenario, now we have 10K topics, and we have 100 megabytes per second across these 100K topics. Now the latency, the green line, which is Pulsar 3.0, looks much better. So the 99% latency is significantly lower. So it went from 90 to 17 milliseconds, 99% latency. So it was a huge improvement in the latency profile here, just by reducing contention and lowering CPU usage there. And in terms of throughput, it essentially it kind of like doubled, more than doubled the throughput from 2.10 and to 3.0. Again, this was across 10K topics. So what is next, and what we plan to work on for next? We have a bunch of ideas there. One of the most impactful one is around the BookKeeper read batching protocol. So it's a new improvement in BookKeeper that's coming up in the 4.18. Essentially, BookKeeper right now, from an API perspective, it has batch read, but the protocol level, it is sending out one at a time. So for catch-up reads, for like backlog draining, it can be used using lots of CPU, again, if you have many small messages. So just by switching that protocol level, having support for batch reads in BookKeeper, we can have many X of more read performance just on the Bookie. A similar one is that we do use Roxyb in BookKeeper for storing the indexes of where the data is located on the disk. So we know that, okay, ledger ID, entry ID, and it is at this file at this offset. So Roxyb has very good performance, but the JNI wrapper in Java has a bunch of overhead. So now, if you have many small entries, means many entries to keep track of in Roxyb, and also a lot of large batch writes and a lot of reads, it can also use a lot of resources. So we did improvements in Roxyb to basically bypass, so to make the JNI cost to be much less by not passing, say, byte arrays instead of passing like a memory location. So we do have netty, which we can use direct memory access. So it's like having a C pointer with netty. We want to basically pass that long address to Roxyb and say, okay, write this buffer that I have here. I guarantee you that it's a valid buffer at this memory address, and use it. And same for read. And this is especially important in the doing write batch. So when we write Roxyb, we just create a batch and then adding many small entries with all the indices and then write the batch. But for each and every item, we have to cross the JNI boundary here. So we made these patches of Roxyb, which we are trying to get them released by the Roxyb community. But like for a single get, we can get like a 60% improvement. But it is but we get a 10x improvement when adding on a single batch. So hopefully we can get these changes released very soon. Almost last one, but we want to extend more usage of batch blocking queue. So with most of the usages right now are internal to BookKeeper, to the Bookie layer. The journal or the callbacks have been moved to batch blocking queue, but we want to apply that approach also a lot more in the broker, like reading many requests in a single shot from one IO thread instead of like reading one by one, like we do today. So read a bunch of them until the socket is empty. When the socket is empty, then we have a bunch of requests. We can send them in one shot to the next thread. Again, the idea is to kind of like miming the batching mode without having batches. So do a bunch of stuff, pass on the next thread, and then do a bunch of stuff again, instead of doing one by one. Now is the last one, which is a support for IO Uring. So basically, IO Uring is a new interface in the Linux kernel to do networking and IO access, which kind of like you can put things to the kernel without having sys calls. In the past, we tried to make it work. All the kernel versions have different bugs. In the end, the performance was not yet faster than using ePOL. But many things were not mature. Kernels, the netty wrapper for it. So we're very confident that right now the situation has changed or is changing quickly. So we want to go back to this and run more experiment with the IO Uring, and it should be very promising to have much better performance, again, with a lot of connections and all these many small messages. So this was all. It was just like a small subset of all the changes that went in the 3.0 and 3.1 for performance-related improvements. But I think it can hopefully it gives a glance of like all the areas that we have been working hard to improve the technology and to make sure that we can keep doing things in a more efficient way. So now, if you have any questions, I'm very happy to answer, or you can grab me outside. I can talk again for this for like next 10 hours. Thanks.